This is a continuation on the properties of light, and I'll be getting a lot more quantitative in this lesson. In other words, I'll be looking at the maths behind diffraction and interference. So diffraction, if you recall, is the bending of light around an obstacle, an edge or a gap, where it basically spreads out. Suppose I have one slit, planar light waves coming through, and the light diffracts, spreads out. Let's take the case of two slits separated by some distance d, and there's some observation screen some distance away from the slits. Suppose light is coming out of the slits at some angle, theta, relative to the horizontal, making its way towards the observation screen. So you have new wavefronts forming. And suppose these two light rays meet up some point x on the screen. Now we can look at this, examine the diffraction mathematically, and the interference as follows. We can find a relation between the slit separation d and the angle theta as follows. Now, because this is 90 degrees here, this angle here will be theta, okay, because you've got 90 minus theta up here, and hence this angle has to be theta down here too. Right, and this is a right angle here too. Now let's work out the path difference. Now the path difference is here. Okay, so the light coming through slit 1, which I'll label by 1 here, and slit 2 here, take different amounts of time to make their way to the point X on the screen. So we can relate the path difference. Let's call this highlighted length delta. We can relate the path difference delta to the slit separation d, and also the angle of diffraction theta, using simple trig. Okay, so let's blow up that triangle here. We've got theta here, we've got d, we've got delta. We can use sine theta is opposite, right? Opposite is delta in this case. Opposite over hypotenuse, the hypotenuse is d. And so therefore the path difference delta is simply given by d sine theta. And the first max will occur when delta is equal to one wavelength, one complete wavelength, right? And the path difference equals one wavelength. The two waves are in sync. Second max occurs when you've got two wavelengths, and so on and so forth. In other words, the differences cancel out to give you a whole number of wavelengths, which is what you want, right, for constructive interference. And let's call the order of interference M, okay, conventionally. It's conventionally labeled M. So maxima will occur when d sine theta, so the path difference, delta, is equal to m lambda, where m is the order of interference, in other words, the number of maxima, and this is a whole number, this is an integer. Okay, so 1, 2, 3, etc., etc. Okay, theta is the angle of diffraction for the mth maximum. So let's see how this thing works. Let's do an example. Suppose I have an incident. Suppose I have a incident light of wavelength 400 nanometers on a double slit. as follows. And it produces an interference pattern on a screen, which looks like this. And suppose the third maximum, the third bright point, in other words, occurs at an angle of 0.8 degrees from the central max. And I'll draw a better diagram, central max. So the central max is here, okay, maximum peak brightness between the two slits on the observation screen, and then maxima, minima followed by maxima. The maxima that follow the main maximum are a bit smaller in terms of height, amplitude. It's sort of symmetric about the maxima, minima symmetric about the central max. Let's suppose we're asked to find the slit separation. How would we go about this? Well, we simply need to use the formula for double slit diffraction. D sine theta is m lambda. This is the double slit diffraction equation. So we need to find D. Simply rearrange using algebra. M lambda is equal to sine theta. Let's plug in. Now we're asked, so M in this case is 3. Okay, third max, that's why we need to put 3 for M. 3 times the wavelength is in the question, 400 nanometers. Now 400 nanometers, the SI units for wavelength is meters. So I have to convert that to the nanometers to meters. So 400 times 10 to the minus 9. Okay, because 1 nanometer is 10 to the minus 9 meters. Divided by sine, angle theta is 0.8 degrees. And you do the calculation, you get an answer of 8.59 times 10 to the minus 5 meters, okay, to 2 decimal places. Now I should stress here that the separation between the central max, right, so I have to sketch the central max, and about that central max you've got maxima, minima, that are symmetric in terms of size and shape. The separation between the central max here and the nth order maxima in the interference pattern is inversely proportional to the slit width. And you get the diffraction pattern spreading out, okay, and the separation between the central max and the other maxima would increase. Okay, so suppose the distance between the slits and the observation screen is L, okay, and the slit separation is D. You can find well, I should say, taking y to be the distance between the interference maxima, right, which is from the center of each maxima. So the central max in this case, the center of the central max and the center of the first order central max, or first order max I should say, to the right and left of the central maximum. The distance is given by y. And taking m to be 1, okay, so the first order maximum, right, after the central peak. So taking m to be 1 corresponding to these two maxima. You can often find there's a bit of tongue twisting involved with these words. So I'm doing the best I can to explain it. So taking m to be 1 for the first order maxima, you'll simply get d sine theta. Okay, because m lambda is just equal to lambda in this case, right? And that's equal to d sine theta. Now noting that for very small angle theta, you'll find that sine theta from basic maths is equivalent to tan theta, is approximately tan theta. And that equals to y over L. Okay, taking this to be y, because for the first order maxima about the central peak, you'll find that y corresponds to one complete wavelength, right? So y is equal to d sine theta, which is just equal to lambda, and you get y over L because if you take this triangle here, y-angle triangle, theta, okay, you've got y, right? Distance between the interference maxima. And you've got L, the distance between the two slits in the observation screen. Tan theta is simply y over L. And so that's for very small angle theta, angle of diffraction. You've also got these interesting things called diffraction gratings. It's basically a periodic structure that diffracts light, okay, to give you an interference pattern. And you typically have a larger number of closely spaced parallel engraved lines, okay, on some material. Could be glass, could be metal for that matter as well. And diffraction grating is just something beyond the syllabus, pretty useful in astrophotonics, a very hot topic in modern astronomy, modern discipline of astronomy. Basically combines photonics, the study of light, and astronomy to picture astronomical objects like galaxies and stars using very sophisticated instruments. So very useful in astrophotonics. Diffraction grating typically looks like this. So there's lots and lots of slits, could be up to hundreds and hundreds. So anything that has more than two slits is called a diffraction grating. And diffraction gratings are great because you get brighter and sharper light coming out. Okay, due to the maxima coming from many slits rather than two slits occurring. So you have a lot more maxima and hence a lot of light coming out. Just as before, you'll have central max corresponding to m equals 0. So I forgot to mention this before. Central max occurs when m equals 0, and you've got symmetric maxima about that. All right, m equals 1, m equals 1, m equals 2, m equals 2. So let's do an example involving a diffraction grating. So let's suppose we have some particular light passing through a diffraction grating. And suppose that a diffraction grating has 1,000 lines per centimeter. And you've got light of a wavelength coming out of it at around 500 nanometers. And we're asked to find the separation between adjacent slits in the grating. We have to find D, in other words. So let's do it. So D, so if there's 1,000 lines per centimeter, then the distance between each pair of lines is simply given by 1 centimeter, which is 0.01 meters, divided by the 1,000 lines. Okay, remember we're working with meters. SI units for distance is the meter in physics. And we get 1 times 10 to the minus 5 meters. Now suppose we're now asked to find the angular spread of first order interference. In other words, the angle, the diffraction angle when light is passed through the grating. Okay, need to find the angle theta. What do we use? Well, we use the diffraction equation. M lambda is equal to d sine theta. Now, first order corresponds to m equals 1. So let's plug in m equals to 1, which is 1 times lambda, which is lambda. We need to find theta. So rearranging, let's rearrange sine theta lambda over d, and therefore theta, to find theta, we take the inverse sine of lambda over d. And we work these out, we worked out d from part A. Inverse sine, wavelength of light in this case is 500 nanometers. SI units are to be in meters for wavelength. So 500 times 10 to the minus 9 over distance d, which is 5 10 to the minus 5. Calculating that, you get 2.87 degrees, roughly. 2 decimal places. And that's how diffraction works quantitatively. So it's a very simple formula. Just trying to getting your head around these mth order interference effects as well. It's very important because that's how you can really make use of this equation. It really helps to understand the fundamentals of diffraction and interference before you get into the maths.